So should I get it up here? Okay. Oh yeah, how do I do that? Just
Yeah, I've got it pulled up here. All right, that look good. You have the slide advancer there, but you just need to make sure you're talking into a mic.
stay grounded.
Welcome, everybody. We're about ready to get started here. Welcome to Restoration and Impact Assessments concurrent session. Runs until about a little after 11 o'clock this morning. And our first speaker is Michael O'Driscoll from ECU. And his talk is titled Bringing Light and Life Back to a Buried Urban Stream in North Carolina Coastal Plain. These presentations are scheduled to run about 20 minutes in total with questions. So we should have a little time at the end of each for a question or two.
Okay, well, good morning, everyone, and welcome back. It's good to be back to in-person conference for sure. And so today I'm going to talk a little bit about some of the work in Greenville, North Carolina, looking at a pretty big project the city undertook, and we sort of worked with them to help monitor some of the new green stormwater infrastructure. And I'll kind of focus in on one neat part of the project was daylighting a buried urban stream, and they installed a regenerative stormwater conveyance along the stream. So we'll take a look at this and how it sort of brought some light and life back to this urban stream. So I think a lot of us can recognize that city life can be hard. And one of the reasons is because we have expanding impervious surfaces. So these are just some examples from Greenville. Some of our parking lots, roadways, buildings, and sidewalks, and some of the alterations to runoff and stormwater generation can impact our urban streams. So they've kind of come up with this idea of the urban stream syndrome, where it's pretty common across urban areas where with a lot of impervious surfaces, you generate flashier flows, you affect the stream channel morphology, and this ends up really impacting the aquatic ecology. So this is kind of one thing that we have going in Greenville as well as many cities. So people started to recognize this, that a lot of our streams in urban areas are buried. And so when you walk around an urban area and you don't see streams in the coastal plain, there may be a stream, but it's underground underneath you. People call these ghost streams and urban stream burial, and they kind of affect some of these headwater stream processes that we see, such as providing clean drinking water, aquatic habitat, and nutrient processing. When the stream's flowing through a concrete pipe, there's not much opportunity for nutrient processing. Some examples of studies where they've really tracked this, like in Baltimore, Maryland, they found about 66% of the streams were actually buried. And so we have this small reach in Greenville where they decided it would be practical to daylight the stream, that segment of the stream. And so we'll talk a little bit about this today. But this is looking at Town Creek. This is in Greenville, North Carolina. And originally, based on some of the earlier maps, we found the stream would have been about a mile long. Now it's only about 1,400 feet long, and a lot of the stream still flows underneath the city. So just going back in time, back in the old days, early 1900s, If you put together the Sanborn maps, they put these together for insurance purposes earlier, and you can see the town creek would have flowed through uptown Greenville all the way over past 10th Street, so pretty extensive. You could imagine now it's pretty densely populated city, just kayaking all the way to the Tar River. So now a lot of this is buried except for that darker segment there. And so when we started to look into this, we were able to find some older maps, and you sort of see that most of the stream length is buried by the 50s, but this 1930 map was real interesting. If you blow up, it used to be that it was ECTC, East Carolina Teachers College, and you could see the map where the river was flowing through campus, and then they forget to include it in this section. So we think this must have been right around the time where they buried it. In earlier maps, you can see the stream flowing, and then you start to see it disappearing on the maps. So it looks like it was buried around the late 20s, at least segments of it. And with that, so you bury the stream alive, and the impervious area is expanding over time as the city of Greenville grew. And it really tracked with ECU's growth as far as the city population and expansion of impervious surfaces. And so this is sort of what Town Creek looks like now. So this is the old culvert system. So some of those bricks might have been from way back in the 20s. And there were challenges where some parts were falling apart, basically. So the city did a really big project to help improve this culvert and include a lot of green stormwater infrastructure as part of that effort. But about 66% of the land surface is draining to Town Creek is impervious. So you can imagine a lot of stormwater challenges. Just looking at some of the common metrics when you look at watershed impervious cover, and if you think about what it was like back in the 20s and 30s, houses were pretty spread out. There wasn't much asphalt. And so condition might have been pretty decent, but then tracking over time, as impervious area expanded, sort of like the band, things are moving in one direction and the condition declined. There's some other issues, challenges with leaking underground storage tanks. And so just a lot of challenges when you have that much impervious area to have a stream with decent quality. So part of these efforts that the city undertook were to kind of look and see if you could start to take it back in another direction and make some improvements. So what I'll do today, I'm not going to focus on the bigger, broader efforts, but just look at some part of the project that we were able to help out with, looking at this daylighted stream segment and regenerative stormwater conveyance that was included. And we also had some funds to create a forested riparian buffer on the stream reach down below this. So before the project, we would go out and that first picture is what you'd see if you're looking at Town Creek. So it's a pipe and you could listen and you could hear it and you could go to the end and see the water flowing out. And so then right around 2018, they started the project, and in 2020, they were able to daylight it a little bit before that. So you kind of start here. Someone said, "Let there be light." And then the stream finally saw daylight. So probably since the 1930s, it hadn't seen daylight at that reach. And W.K. Dixon and co, Mark Horstman designed this pretty large regenerative stormwater conveyance system that would fill in where the old pipe was and the buried stream was. And so this is what it looks like today. So we'll talk a little bit about that. And just overall, the city's sort of started to move from gray to green stormwater infrastructure. So this is one of the features. It's been very beneficial for ECU to be able to work on this and get our students some experience and out on the creek, one that used to be buried. So just looking at some of the things that the RSC can provide, dissipate energy, stabilize the channel, help treat runoff, and provide aquatic habitat. So we were able to get some funding through the Environmental Enhancement Grant Program to be able to monitor this feature. I'll talk about just a little bit of the monitoring today, some of the interesting things we found. And this is sort of ongoing work. So we're continuing to have classes involved and monitor this system. So one thing, what we would do is monthly, after it was installed in the spring of 2020, we were able to instrument. So of course, COVID's going on. So we were able to get permission to go out and do research and start to instrument this system. We would go out and do monthly samples, and we were able to sample a couple of storms too. And so one thing that looked optimistic at the start too was if you look at the nitrate at the top of the RSC and then you look at the nitrate at the bottom of the RSC, we could consistently see declines during base flow conditions. So that's kind of good news. Then when you look at storms, not really. So it's kind of a flow through system during storm events. And when we looked, just that idea that nitrate concentration declines could be related to dilution. So if we look at the nitrate chloride ratios, we could see downstream that was getting lower, and basically the nitrate's declining, but the chloride is staying pretty similar. So it didn't look like it's dilution. So suggesting denitrification going on in these features. And then just looking at, if you look at the base flow median declines, they were around 46% over time for that 1 year that we were able to look at it. So during base flow, we could consider it a nitrate sink where you're losing nitrate. So that's good news. And kind of similar conditions, a little bit less of a decline for total dissolved nitrogen, but about 19% from the top to bottom over the year. So with some of the loggers in the stream channel, we had one set up right at the top riffle, and with elevation surveys, we're able to see, how high that riffle is. And so how much of the time is the water spilling over the top of the riffle when you get higher storm flow conditions? We're able to kind of track that for the year. And the good news is when it goes up over the riffles, it goes down really quick. So there's so much impervious area upstream. It doesn't spend as much time as you would think when we tracked it for this year record. And of course, it'll vary based on the precipitation that we get, but it was only spilling over the top about 3% of the record. So a lot of the time, it's got pretty good nutrient treatment conditions. So you're like, we sent some algae samples to the state and they're like, is this a river or a pond? And I'm like, it's both. So it just depends when you look at it. So what we saw, and we have more stormwater sampling that we'd like to do this semester, but it looks like you don't get much nutrient treatment during the storm events. And then they're in base flow, those are kind of the optimal conditions. So the other interesting thing that we have to deal with in Greenville is backwater flooding. And we started to notice this. So it makes it a little bit more complicated to get a good rating curve there when the Tar River is right next to you. So it's just a few hundred feet downstream. One thing that's fortunate is USGS has the Greenville Tar River gauge right there at the town common. So it's right around the corner from our site here. But this was an example. We were out sampling in February 2021, and there was a pretty big flood event in Greenville on the Tar River. And so you can see, remember before when I showed images, there's several riffles and you can only see one in the RSC. So the backwater effect actually backed water all the way up. So if we compare our stage data in Town Creek to the Tar River flows, basically it kind of pans out. Once you get about 1.5 feet over flood stage, that's enough to create backwater effects at the point we're at the 3rd Street culvert. And so when we looked for that year, there were about 5 backwater events in the year. One of them, especially if you have sensors that you have to download, you can't get in the water, it's 6 feet high. And so we kind of had to wait a little bit to get some of our sensors out. But that one in February, it lasted about 12 days. So the water's just kind of sitting there until the Tar River drops down. So the other part that we did a little bit earlier with some of the funding was we were able to create a forested riparian buffer. So in 2 different efforts, we were able to plant about 150 trees. So it was pretty much grass lawn to the river channel before that. And so now things are starting to grow and things are starting to look a little bit better there. The other thing, as we go out, so we started to do some undergraduate research courses, and they get to go out there and they start to see, they'll come up to me with little turtles or frogs and some fish in these pools. And then as we noticed going out there monitoring, the RSC, because of those riffles and there's some rebar going across the rocks to hold them in place, they tend to collect trash. So there's such an urban area upstream. So I started to see that, and our sustainability director, Chad Carwine, he said, well, we should get students come out, and he started to get groups together. So they go out monthly and help to clean it up that way. So just some images here of the riparian reforestation project. So everyone was able to put in a few trees, and we got a lot of good cooperation there. So now it's really starting to look a lot better and stabilize the slopes. When we try to get buy-in from facility services, they were really keen on it because now they don't have to mow that grass. And these are some of the steepest slopes in the coastal plain. So just looking kind of before what the condition was, it was mostly grass there. And so now afterwards, starting to get a good forest there right along the stream. I had a little video and then it was causing some issues. So I just showed some pictures. But if you think about it, if this was buried in the 20s, that was when Greenville High School was there. And in that buried segment, there probably wouldn't have been any fish unless you're really confused and you like dark. And so now we're starting to see fish come back. I'm not sure what kind of fish those are, but we've also seen catfish in there. And so I think it's interesting with the backwater effect. It can flood over the pools, and I wonder exactly how the fish will manage in there if it doesn't rain a lot, they can't really get out. So the trash cleanups, this sort of resulted when we noticed it really does collect a lot of trash. Sometimes you could go out there and get 100 beer cans, along the river. So think about what people are doing upstream. We're right next to campus, but it's really interesting to the students too to think about that and the types of trash. One day we were there in the storm. I said, let's watch this runoff. And we saw like a 50-foot garden hose. I don't know how it got down the storm drain. And we watched it flow downtown creek and into the Tar River. But yeah, so this has been going on. They've been able to get out there just about monthly with Chad and some other groups. And sometimes we'll do water quality monitoring when they do the cleanups too. So one thing we really appreciated about this effort is our students have really been able to get out there and learn about water quality, flow measurements. It's right on campus, so it's very convenient. And where it really helped us out, so they installed it right at the spring of 2020. And of course, COVID is going on and they're saying, you can't be in classrooms with people. So we said, all right, we'll meet out there. And the students really liked that. So we would do like one class lecture online, and then one class we'd be out there. And I asked the students one day, I'm like, aren't you tired of all this Zooming on COVID? And they're like, no, we actually like to be at home taking our class, and then you come out there and you get to meet up with people and do some work. So that part was a really huge benefit. Just since last year, we started to do course-based undergraduate research projects on the creek. So things like dye tracers and monitoring water quality, students working with loggers and things like that. Yeah, so just kind of summarizing then, I know I'll run out of time here shortly, but a lot of our urban streams are often neglected, and you might not be able to fully restore them, but there's a lot of benefits you can get from these types of efforts. They're still kind of looking at some of the flood reduction benefits for the bigger project. And based on our precipitation, it's been pretty low lately, but they used to have quite a bit of flooding in uptown Greenville, and there haven't been reports of that lately. So we'll see when it gets wetter. Some water quality improvements we can see. And then the other thing that people comment on is just some of the improved aesthetics. So before you were looking at a concrete pipe, and now people go there. The city has plans now to set up a greenway there. And so we're going to be able to have like a little educational kiosk next to the creek. So it looks like I better finish up here, but we really appreciated it. And the ability to have educational opportunities throughout this project. So yeah, thanks for your attention. I think I've run out of time.
Thank you, Michael. He'll be available for questions after the session. Next presentation is Kristen Navaroli from WSP USA. Title is Pilot Facility Level Climate Change Adaptation Assessment for Little Indian Creek.
Hey everyone, my name is Kristen Navaroli. I am a water resources engineer with WSP in our downtown Raleigh office. And today I'm going to be talking to you about a climate level assessment we did for the Little Indian Creek culvert. I always like to start this off by saying this is truly a team effort. We had people from coast to coast, engineers, scientists, planners working on this to make it a success. It was an incredible project and we wouldn't have been able to do it without everyone else. So I like to start off with a roadmap, where we're going to go today. We're going to start looking at our project location, where we are in California, then zooming in, taking a look at our watershed, looking at our culvert, the infrastructure, and then starting to build those climate variables, those climate simulations before getting into the hydrology, hydraulics, and then the decision-making process we had at the end. So getting us started, where are we? We are in Northern California, Plumas County. We're in the crest of the Sierra Nevada mountain range, which becomes increasingly important later on. Caltrans District 2, we're under a state road that connects those eastern mountain communities to those western mountain communities. And these mountain roads become increasingly important during winter months when snowfall does become a factor. So continuing to zoom in a little bit, we're looking at our watershed. At the top right, we have our Little Indian Creek watershed. As you can see, it's very long and narrow. There's about a 5,000 foot elevation difference from the crest of our mountain all the way down to our valley. So it's pretty deep. And also very importantly, you can kind of see where the yellow marker is. We're at the confluence of a very large river, the North Fork Feather River. Again, I'll elaborate this watershed a little bit later, but we did include it in our analysis for a backwater, and it proved to be a good call. All right, zooming in a little bit more, we're looking at our culvert. So a traditional concrete culvert, the end walls and head walls had been replaced and changed over the years due to storm damage. However, through inspections, they decided it was a fair condition. Caltrans does not have any intentions on replacing this culvert unless it's severely damaged. So we actually brought our analysis all the way out to year 2099 to see how this is going to function in the future and what kind of investments we need to make now that will make us successful out 80 years from now. All right, still looking at our culvert, that beautiful rushing river in that top right photo. That's if you're standing on the roadway. This took place in 2017. A massive storm event came through, and that was water overtopping the road. So they have proof that in the past, massive storm events have caused significant damage. As you can see in the left lower photo, there was guardrail damage, shoulder damage. There was some cosmetic damage to the culvert, but it took several days to a couple weeks to get this road back in operation following a storm event 5 years ago. So now we've seen that the culvert is impacted by stormwater. Now we need to start building those climate scenarios. So California's fourth climate change assessment has determined these four models, these four global climate models, GCMs, we're good at looking at what the state's climate is now and also moving through the future. So HADGEM is your warm, dry climate. CNRM is that cool, wet climate. And then those final two are kind of intermediates. So we're casting this wide net of possible climate scenarios because we don't know what's going to happen in the future. We want to make sure we're covering our bases for all of our flows moving forward. Supplementing our GCMs, we have representative concentration pathways, or RCPs. So RCP 4.5, you're looking at those lower greenhouse emissions. So if we start doing the changes now to lower them in the future, RCP 8.5 is kind of like we don't make changes now, and we just let it happen. We're going to have a little bit of higher emissions moving forward. So again, we're widening that net of future possible scenarios. So in total, we had 8 climate scenarios. Now looking at our variables. So for each of those 8 scenarios, we then had these 5 variables that I'll go into a little bit more detail that built our hydrology and how we're going to look at flows through this watershed. So starting off with temperature. Our temperature determines the precipitation type. How is water falling on our watershed? So we looked at rain, a wintry mix, and then snow. And then, of course, precipitation depth, how much water is falling on our watershed. I mentioned we're at the crest of the Sierra Nevada. This is why it was important. So to the west, we had that wetter windward side at Bucks Creek. These are NOAA gauges. And then to the east, we had that drier leeward side, which is the Caribou Station, in our watershed, smack dab in the middle of it. There was a significant difference in precipitation depths between these two, and we didn't have a rain gauge at our watershed. So we ended up going with Bucks Creek to be a little more conservative, just based off of what we've seen in historic trends at this watershed. And these are the super cool scenarios. Snow water equivalent is my favorite. So it's how much water is being held in a snowpack. The best way to describe it is if you have that fluffy, powdery snow you like to go skiing on, that's gonna have a very low SWE. There's not a lot of liquid water in it. Versus like the slushy snow that you have on the side of the street that sprays everywhere, you're gonna have a much higher SWE. So the greater your SWE, the more flooding potential you have. And we looked at a range of temperatures and SWEs as we built these climate simulations. Then also we have wildfire. So wildfire is not an output of GCMs. So we used CalAdapt's website and worked with CalAdapt to look at historic burning of our watershed and also what they're forecasting for the future. And wildfire, it changes your watershed, it changes your vegetation, soil starts to become hydrophobic, and it dramatically increases these flood flows, but also debris flows that you have to take in consideration with your infrastructure. So now we get to build our climate simulations. So we had 2 different hydrologic simulations. We built them in EPA swim, first being rain on snow. So we had a bunch of different temperatures, a bunch of different size snowpacks with those varying SWEs. That was one simulation. The second simulation is going to be wildfire. So using the amount of watershed that's going to burn, we created a statistical relationship to determine how we change the curve number of the watershed to kind of represent that. We assumed that it takes 10 years for a watershed to fully heal. So if you have a fire, it's going to linearly stair step down to heal. And if you have a fire halfway through that, you're going to go right back up and have to take the time to heal, which we'll see a graphic later that shows that really well. And as you can see on this picture and to the side, that watershed, you can see where it's burned in the past. Those kind of beigey areas are burn scarred landscape. It's hard to see in the projector up here, but in the channel, you can see like full logs that have been burned and just washed right down into the stream. So there's definitely history. And, oh, it just burned a couple months ago. There was a wildfire in this watershed a couple months ago. All right, this is my favorite graph. It displays everything that we wanted to show with this project. So the black line is your traditional rain on land and your peak flow. So we're looking at your rainfall inches compared to your flow. That's your traditional hydrology. And then you look at this dark red line that scoops all the way up, and that's your fire. So if we start looking at the watershed burned, we put the same amount of rain on it, what are your peak flows going to look like? And then you see these pockets of colors. So the colors are different temperatures. The pinky purplies are the 70-degree rain. And then down at the bottom, those like yellowy beige colors are those 40-degree rains. So you can see that change in peak flow dependent on how warm the rain is compared to how big the snowpack is. And you start to notice that some snowpacks are less than the rain on land traditional hydrology. And the best way to think of it is if a snowpack was a sponge. So you have a cold 40-degree rain falling on an 80-inch snowpack, it's not going to melt as fast, and it's actually going to hold some of the water up in your watershed and slowly delay it. So now you have a completely different hydrograph than you would if you had a 70-degree rain. With this project, we did only look at 24-hour periods, but one thing that would be super cool to look at in the future is if we looked over 5 days, a week, like what these flows would look like. All right, so we run all of our peak flows for all 8 simulations. We do statistical analysis, and then we start coming up with charts like this. So I pulled HADGEM. HADGEM is that warm, dry scenario. And this is from year 2096 all the way to 2099. So I like to emphasize the last quarter of these graphs. So you have in your RCP 4.5, again, low emissions. You do have an instance of fire, and you see that stair step that I mentioned earlier, where it started to heal, you had another fire, goes right back up, continues to heal. The blue is rainfall, so your rainfall depths, and then the green, which you can kind of see, snow instances. So 4.5, again, the same time period, now 8.5, those higher emissions, we have twice the amount of fire instances. And again, you're seeing that stair step healing. The blue is significantly higher, and there's about 2 instances of snow. So we're seeing a dramatic change just from changing the greenhouse gas emissions and what that does to our watershed. All right, so at the beginning I mentioned we were at the confluence of a much larger watershed. So we're gonna bring it back up. Little Indian Creek was about 5 square miles. North Feather Fork River is about 1,800 square miles. It spans almost to the border of Nevada. It's massive. We could not do a climate assessment the way we did here on that level. Just the assumptions wouldn't be the same, scope of the project, all of those good things. So we created a timing relationship looking at if it were to rain in our watershed using traditional storm patterns, and then it were to rain on this larger watershed, what the peak flows are going to look like when our watershed peaks in this watershed. So we created a backwater effect using this timing relationship. And this is why it was important. So the top left graph, we're looking at just our watershed. Like if we put our hydrology through, this is of course one instance. If we put our hydrology through, at what point are we going to overtop the culvert, overtop the road? Now we put in the backwater effects of the larger watershed, and those instances drop. We're getting less than a 10-year level of service once we consider backwater effects. So now we know what our culvert is doing today with all of these different climate scenarios. How do we remediate this problem? So we came up with 3 alternatives, varying levels of investment like we typically do. We had our Band-Aid approach, low cost. It'll get you where you need to be for the next 10, 20 years, all the way to your Cadillac of we're putting in a massive bridge, we're raising the road, water will never cross this road ever again. Now, where do you find that medium investment that you can propose to your client and not sound ludicrous? We conducted an economic analysis. So as part of our sustainability team, we have people who do this all the time, and CalAdapt does have parameters that we were to follow. But we looked at not only the infrastructure investment of the culvert, the roadway, the shoulder, the guardrail, but also the socioeconomic investments of, so we're about, where it says about Belden, I mentioned those eastern communities need to be connected to the western. That's about a 3-hour detour if you need to get to the city to the west, when it should have been a 45-minute drive. Now with gas prices the way they are, I'm sure our economic assessment would look a little bit different. So this was a heavy influence in our decision-making process. Also a depth damage cost. So looking at when it floods today, you get this many inches of water over the road. It's going to take about 2 days to fix versus If we do this option, now you get to delay that a little bit more. Now let's bring it on home. So what does this mean? A key takeaway is hydrology can be so much more than rain on land. We used EPA Swim, a free program. It had snowpacks, temperature, CalAdapt had the wildfire. You can start building these more holistic watershed models, incorporating some climate data. And also looking towards the future, what infrastructure investment decisions do we need to make? We can band-aid it for the next couple decades, or do we want to start looking out 100 years in advance with our infrastructure decisions? So with that, thank you all so much. My name is Kristen Navaroli. I put my email up there, so if you have any questions, please feel free to reach out. And I think I left some time for questions. Cool.
Yes, we got time for questions. If you have a question, would you please approach the microphone here and ask away?
I know that was a lot of information in 15 minutes. It's a doozy.
I had a question, but now I can't remember what it is. Give me a second.
Right? Like
We
it
got
goes
enough
so
time
fast,
for-
you're like, oh no. And of course, I have my email up there. So if you think of it in a couple days, please feel free to reach out. Anyone who knows me knows I will always talk about this project. So.
Oh, I remember my question. It looked like you had some HEC-RAS models there. Was it did you do just one-dimensional modeling?
Yeah, it was just a 1D culvert model. Again, we did the hydrology and swim, put those flows in a 1D model. But it'd be pretty cool to see it in 2D.
Excellent. Yeah, I don't know how to, I don't even know how to open 2D, but I can hack around in
It's
1D
pretty
a little
cool.
bit. Yeah.
It's pretty cool.
We have another question.
Hey.
Hi, just a small question. So you said you assumed 10 years for wildfire restoration.
Yes.
Was that based off of previous observation in that area, or where does that come from? And things like larger fires, like is it the same time frame?
Yeah, so that's a really good question. That's an area, unfortunately, there's not a lot known about wildfires and how it affects watersheds. And that's why we're doing studies like this to see, can we bring a little more research into it? So we did as WSP did a project out in Colorado where they did a huge literature search and came up with a 10-year analysis. We then brought that to California and we're like, hey, based off of what you guys see, because it happens kind of often in California, do you agree with this assumption? And they did. That is one area that we really want to research further, though. We tried to get a little bit of funding to see if we could. We used CalAdapt's fire modeling, but there's also dynamic vegetation models. They just didn't have it in our project site. We kind of wish they did. But it looks at like the severity of the fire and if that healing would be different. So it's an area that we want to look into more. Good question, though.
Yeah, thanks.
Good. Thank you.
Thanks very much, Kristen.
Okay, how you doing? Is this a pointer?
Yeah.
Yeah. That's me. Yeah. Okay.
I'd like to introduce Greg Melia, NC DEQ. And his presentation is titled Factors Determining Thresholds of Reliable Change Detection in Water Quality Resulting from Stream Restoration, the question of signal to noise.
Thanks, Zach. Again, my name is Greg Melia. I'm with the Division of Mitigation Services. We are one of the larger providers in North Carolina of compensatory mitigation. I assume folks know what that is, but if not, just in a one sentence thing, it's when we can unavoidably impact streams and wetlands, you have to restore degraded systems within some distance in order to compensate for those impacts. I'm going to be talking about some work that we're doing, some water quality assessments that we're trying to examine and go over the drivers for that, as well as the objectives, and focus in on one in particular in trying to assess this concept or this question of signal to noise. So the history and the drivers are several, of course. Water quality improvement is often stated in mitigation plans for restoration, but it is not that frequently measured directly. And that the functional efficacy of restoration for something like pollutant attenuation in the absence of watershed controls has been a topic in the dialogue, in the literature for some time now. The last decade has shown a range of results, but we still need a better understanding of the effects of scale, the setting, and the specific practices and how they and what they can achieve and in what time frame. In addition to these drivers, there's been some regulatory-based drivers. In 2008, the EPA and the Army Corps of Engineers released a revised mitigation rule requiring, quote, ecological performance standards. Now, they don't highly define that in that document, but it represented a sort of shift from very little guidance or focusing on physical assessment of these systems to maybe getting more complex endpoints, ecological endpoints, and things of that nature. In turn from that, the North Carolina IRT, which is the assemblage of agencies that oversee compensatory mitigation in North Carolina, they actually encouraged and incentivized water quality assessment in their 2016 update to monitoring. And so these collectively have kind of been the history and the driver for us starting to look at this within DMS. So again, I said, we're in a position, we're a large provider of mitigation. We have an opportunity for long-term observation and monitoring, and that's another facet, is that you maybe want to look at really how these sites develop over a longer period of time. And our program is tied to a robust watershed planning approach. So our objectives in this work are several. We want to provide a set of case examples within the settings and the practices that are employed in a mitigation in North Carolina, and gain some understanding of the relative efficacy of different practices and the timeframes at which we can expect to see improvement and how sustainable they are. We also want to utilize the data to potentially refine current simple models that appear in our mitigation plans for pollution reduction estimates. But today's talk is going to focus on objective 5, which is trying to gain an understanding and describe what we are going to collect as other data streams to try and characterize signal to noise along a gradient of different scale, different practices, different settings. And then try to gain an understanding of, given those factors, what sampling regime might be necessary, what level of effort might be required. So just quickly, I think most folks are familiar with the concept of signal to noise. It's basically the separation or the differential of the relative magnitude of what you want to measure in a measurement system versus the background noise and variation. The larger the difference in these magnitudes, the greater resolving power you have, the greater likelihood that you can reliably detect change. So we're trying to look at different categories of the stressors and the land use, land cover within the context of reach and watershed restoration. So we're trying to look at the spatial distribution of the stressors, the stressor areas that exist within these watersheds, and the proportions of stressor areas that get treated as a result of our work and our initiatives, our treatments, if you will. And secondly, we're also going to track stressor intensity. Not all an acre of land use, land cover of pasture or row crop is not created all the same. And there's different level stressor intensities that are resulting from that. And then stressor types, things like, are we talking about impervious cover? Are we talking about row crop in an ag setting? Are we talking about pasture in an ag setting? So those first two that I just showed, the distribution of the stressor areas and the proportion of treatment combined with that stressor intensity kind of alludes to an overall stressor load, not in a rigorous sense of a measured load, but saying this is the distribution and intensity of stressors within and outside our treatment, our area of control. And so the larger proportion that exists within our treatment area and the more intensity that is in our treatment area, the higher the signal to noise is what we expect to see. So just to give you an example, one of the projects we've just initiated is it's a synoptic nested sampling system with, we're using ISCOs, and my colleague later will go in detail about one project and talking about our methods and our results for that. But you can see these two neighboring watersheds in this here, the yellow and the gray, they're about the same size, 160 to 189 acres. But as I'm going to try to contrast and show, looking at those variables we're talking about, if you examine the station 3 here that you see, first of all, the red is our easement. So that's our treatment area. And the land use, land cover types of interest here are forested pasture, open pasture, and row crop. And if you examine the total amount of stressor area draining to station 3, that treatment station, 54% of that, of the total for this entire highlighted blue watershed is occurring within our treatment zone between station 5 and station 3. So station 5 being our upstream control station, being a sentinel for the contributing watershed when we're going to compare pre and post. But that intervening space between 3 and 5 is housing 54% of the ag stressors within the entire watershed. Another variable or another attribute that we're looking at is what percentage of the drainage network does our restoration reach actually treat. So in this case, between 3 and 5, you're looking at about a 12% of the drainage network is being treated. So these numbers aren't necessarily low in the context of the full range of watershed sizes, but I will say in mitigation, and especially as it has evolved over the last decade and a half, where we are really working more up in these uber headwater systems, and we are working in smaller drainages. We've learned some lessons in the past about trying to work with, high order urban streams in the coastal plain, for example. So then looking at the neighboring watershed, that upper watershed. So even though those proportions were not small, they are moderate in comparison to what we're looking at here at station 4. So in this case, between station 6 and 7 and 4, we're treating about 82% of the drainage network that's in this. So that's quite high. And 96% of the ag stressors draining to station 4 are in our treatment zone. So we're looking at a very high signal to noise condition here. And so I just wanted to provide that contrast of that, we're trying to find reaches that'll present a gradient of these factors so that we can have a set of case examples that would be informative. Then looking at stressor intensity, again, like we're saying, no pastures are all the same, no row crop is all the same. We're tracking what the stocking densities are, when and where the cattle are being rotated, crop rotations, that sort of thing, to have the sort of timeline of what happened when in relation to our restoration efforts. And here's an example of some data from 2 of our projects pre-construction, looking at total nitrogen, where they were both pasture, land use, land cover. But you can see that the distribution on the left is quite a bit higher than the distribution on the right. We had different levels of pressure, different levels. So we're going to try and figure out, maybe what the range of this could be for different of the major stressor land use types that we're dealing with. So looking at historical orthoimagery and having discussions with landowners regarding the land use history, and as I said, application rates, rotation schedules, trying to see what's happening when and where. That third category, looking at the type of stressor, in some cases, like here, if you have a sort of a row crop stressor that's somewhat removed from the stream itself, but over space at a longer period of time, you may have a reservoir of something like nitrate in your groundwater that isn't going to shut off as a result of what we're doing. And the fertilizers are still going to be applied and outside the system. And it's just another way to understand what to expect with regard to what's achievable in mitigation and in mitigation timeframes. So I just want to go over as an overview the sites that we're looking at. Most are in the Piedmont. We'll be adding additional ones as time goes on. One of them is in Sandhills. Some of these sites were assessed by our academic partners. So for example, Heath Dairy, that was assessed by NC State, Dan Line and Jamie Blackwell. It had a decent amount of pre and about 1.7 years post. This also had the ability, Heath Dairy and Millstone were both NC State, and these are a different type of procurement from our the way we procure projects, and it gives us the ability to tease out the effect of, say, cattle removal versus channel modification. And that's Dan Lyons working on that for both of those. The Heath Dairy one there is a publication for it. It's in the citations at the back, but we're trying to add to our inventory of case reaches and case studies to characterize this gradient. Backwater is one that we did up in Hillsborough, which my colleague Danielle Meir is going to go in detail on with results and our procedures. Big Harris is a larger project that Western Carolina is working on for us and assessing those parameters there, fecal nutrients, et cetera, and biology with macrobenthos and fish. And then these other projects, which we have pre-data for, but not anything yet post-construction. So in conclusion, we're going to continue to add reaches of varying scale and complexity to provide an adequate gradient of signal to noise to identify the factors that might inform detection expectations and assist mitigation practitioners in grouping reaches of their projects and subwatersheds in coarse bins of likelihood in terms of reliable change detection. Right now, this sort of the goal setting occurs at a project scale, and it's not granular enough to really answer some of these questions. So it may be in the future that with the help of data like this, that folks are really talking about sections of their project and what they can achieve and what they can do versus it being blended completely at the project scale. So that's an overview of what we've been doing, what we're up to. Like I said, Danielle will give you an example of a more recent one that we have where we have pre-post data. I want to thank the SNA staff, our academic partners, and the mitigation providers that we work with on their projects. And I just have some citations here. I think these provide a good overview of the discourse and the discussion with regard to restoration in the last 2 decades. So if anybody has questions,
We have time for questions. If you've got a question, please approach the microphone here. Yeah, we got a little time for that.
Okay, well, I'll be available after if anybody has additional. So
I have a question, Greg.
Yeah.
I just, I was looking at the maps and I like the paired watershed. That always kind of gets me thinking and imagining different places I've worked. Have you guys looked at in terms of, I guess, land use history and potential, drivers for signal to noise, any kind of soil mapping or soil quality information?
Acknowledge that there's more factors than this that we need to look at. We need to look at terrain, valley morphology and things like
And soil, yeah.
It's quite honestly, there's, as you would think, a lot of variables.
Yeah.
And I don't want to overstate what we might be able to do in terms of making some kind of refined predictive model versus providing case examples that may fit into like these course bins that practitioners could use but those other factors are things we'll be looking at. So like, the effects on phosphorus or things like that with the different.
Well, it could, and it could be on a smaller scale, like these watersheds that the soil is essentially uniform. I mean, if it's had pasture land, I mean, forest versus pasture, of course, could function differently, but it might not be that complicated on a smaller scale. So that could be good. You might be able to
those would be other, categorical variables.
Great. Anyone else have a question?
Thanks for your attention.
Thanks, Greg.
Appreciate it.
I'm the last one. Hello. Good. Nice to meet you. Yeah, do we have to wait? Okay. Oh, okay. We could wait a little bit. Okay. Yeah, do let me. When I practice it, it was between 15 and 20. So just if you can, yeah, that'd be great. Speed it up. Okay. So you said wait a few minutes?
As moderator, I read my instructions just now and realized that we're not supposed to start early, so we have a little time here. But I'd like to anyway introduce Danielle Meir, NCDQ, and her talk is titled "Are Water Quality Changes Detectable Post-Stream Restoration?" So we'll start in just a couple minutes.
Yeah, then we'll wait. Can I ask a question to one of the previous speakers? ECU, what was his name? What was the ECU speaker?
Kristen?
No,
Michael? Yeah, Michael.
Okay. Yeah. Since we have time, I wanted to ask a question to one of the previous speakers, and wanted to ask you, Michael, when you guys did your water quality monitoring, you were talking about your nitrate, NO3. What kind of meters did you guys use or sensors?
Also, with that handheld monitoring, it's like a side plus. So we calibrate that.
Okay, so the samples were taken to a lab?
Yeah.
Okay, I didn't know because we're looking into having some nutrient sensors for some of our stations or to have our providers use down the road. So I didn't know if anyone had to.
So the nutrient sensors, they're decent for detection downstream. They don't pair out perfectly with the lab, so we trust the lab.
Yeah, and that's what we use. We're just, trying to help our providers maybe do some water quality in the future as well. So just on, I'll ask.
Yeah, so we've sent some samples to the state and said there's some interesting things that Yeah, so when you think about it, it was so dark before, and now it's probably starting to evolve. Growing there, but very local.
I think we're ready.
Is it time?
Yeah.
Okay. Well, thank you all for having me this morning. My name again is Danielle Muir. I'm with the Division of Mitigation Services. And I am here to ask, are water quality changes detectable after stream restoration? So here's a slide I hope you all remember from just a few minutes ago when my colleague Greg Melia went over the DMS objectives for water quality monitoring in our mitigation sites. He did a great job going over objective number 5, the signal to noise. So I'm going to be talking to you about a project, our Backwater site, and it's going to have a lower noise in the watershed. So I'm going to go and try to give insight based on our findings so far on objective 1, basically providing examples of water quality response to stream restoration. And 3, what is the time frame to see improvement and is it sustainable? So since you've already saw this, I'll move forward. So here's a map. I think you guys can see it pretty clear, but to go over it, this is Backwater. Backwater is in Orange County, Hillsborough, North Carolina. This project is a mixture of stream restoration and stream enhancement. The entire project's treated area is about 12,600 linear feet of stream. And if we look here at the map, you could kind of train your eyes to the blue is stream restoration. So all of the blue would be where there was actual stream restoration. Yellow is enhancement 1. Orange, it would be enhancement 2. So these are just different levels of mitigation. The dotted line that surrounds the entire creek is our easement boundary. So everything within the black dotted line is where mitigation occurs. I circled in red one tributary. This is T4, and we'll take a closer look. So Trib 4 or T4, we chose this reach to do water quality monitoring. The entire reach length is 820 feet. The overall watershed, which is in red, and then it turns into orange at the upper part when it mixes with yellow, that is about 74 acres. The yellow watershed is the upper part. So as you see where the star is, which is our upstream site, we call that our watershed control. So upstream of that is only about 20 acres, and it's entirely forested. This trib has a fork, as you can see. This entire trib is mostly restoration, except for that small portion that's orange, enhancement 2. And both of, this entire watershed is captured down at the downstream site. And so our idea that Greg had just explained was we're looking at pre and post restoration. This one, Backwater, we had about roughly 0.8 to 1.5 years of water quality monitoring before they started stream restoration. Downstream had a little less because we had to remove the weir for them to start construction. We were able to keep the upstream up a little longer because it's just outside the treatment area. So then we allowed them to finish restoration, plant the vegetation, and as things started to get a little established, we started our post monitoring, and we're about 2 years right now in that. So again, why did we choose this reach? As I mentioned, the upstream portion is completely forested. So since this is one of the primary projects and the importance of signal to noise, we really wanted to reduce the noise in the watershed. So we have this as our reference. Of this entire reach, there was about 30 acres of that 74 acre area of the watershed that has stressors, and 68% of those stressors were being treated within the watershed. And what are some of the stressors of the Backwater watershed? Well, livestock was one of the major ones. And this was one of the main lateral drainage stressors in Reach T4. This was pre-construction, photos courtesy of our provider. Cows just roamed in and out of the creeks, no problem. Then we also had a eutrophic pond. This pond had drained straight into Reach T4. And of course, with that was adding nutrients to the system. And then we also had floodplain disconnection. Reach T4 was incised, and those are our major stressors. So we set up water quality stations. So first we chose to use ISCO auto samplers. Our main purpose behind using an ISCO auto sampler was first and foremost to avoid storm chasing. Anyone who's done storm sampling knows that that can be pretty intensive. So we were able to program these ISCO auto samplers to collect flow proportional composites, which means every so many gallons passed, we would get a fragment of sample and then we composite it over a certain time period. We were also able to tell it to sample at different stages. So we would say, okay, Baseflow is under, 1 foot. Anything under a foot of, water level is going to be considered Baseflow samples. The sampler will collect those in the designated bottles, and then we'll tell it above a certain stage, you're going to be stormwater. So we did both storm and Baseflow. Discharge, the ISCOs also can calculate discharge based on stage by us inputting a rating curve for that site. Our rating curves, we would either derive it from WRRI equations or dilution gauging. We have now moved towards dilution gauging, and we are no longer using WRRIs. WRRIs are very accurate for like culverts and other areas, but for these stream mitigation sites, since it's open water, many times you'll have crayfish crawling in under it. We're constantly having to reseal it. You're not getting accurate discharge anymore. It's really not appropriate to probably install a WRRI right after stream restoration. It kind of defeats the purpose since you're actually building a structure. And it also likes to attract a lot of wildlife. We've had game cams out there and it becomes a hangout. And, with wildlife hanging out, you're probably also changing your water quality and fecal concentrations. So dilution gauging is a very easy method. It could be used for multiple things. And I highly encourage you all to watch a presentation on dilution gauging by our colleague, Joe Familaro, tomorrow at 9:10. So it has multiple uses. 9:10, Joe Familaro with DMS. Anyhow, we'll go back. Then the ISCO can also integrate precipitation data. As you see here, there's a picture of a rain gauge that's wired into the ISCO. And then we also have the submersible probe that will do stage level. So that's why we use an ISCO. So when we set up our station, we would do a cross section to get an idea of the characteristics. We would install a stage plate. Stage plate will help us keep our stage meter calibrated and to know the level. We secure our sampling equipment into a yard box. And if you notice, it's not just securing it with a yard box or having to lock it up like maybe I did in urban streams. This we want to wire around to kind of keep the renegade cows from knocking it over. And then we'll program the ISCOs. You see my colleague Greg there, out in the winter, nothing stops them, programming away. And then again, our site-specific rating curve that we program into the ISCO for every site and to get our discharge. So now into the data, my favorite part. So here, I'm going to show you guys a bunch of box plots. They're all going to be set up the same way. On the y-axis, I'm going to have our parameter of interest. This case is total suspended solids in milligrams per liter. You're going to see on the bottom of on our x-axis, you're going to have two groups. It's going to be the upstream For Backwater, the upstream, for most of our stations, the upstream will be our control station, our watershed characteristics prior to restoration, outside of the restoration area. And the second group is going to be your downstream. Above them, I have our N values, total number of samples within that calculation. We'll train your eyes that blue would be our pre-study. This is before any restoration, and green would be after our restoration. My p-values were calculated using the non-parametric Wilcoxon sum of ranks. And so here for suspended solids, we'll see there's no change upstream. That's a good thing because that should be our control. And downstream, we see a huge, highly significant difference with a median change of 74% reduction in the post study for total suspended solids. Now total phosphorus, same thing. Total phosphorus in milligrams per liter, we have no change upstream, but we do have a highly significant difference between pre and post downstream with a median change of 79% reduction in total phosphorus in the post study so far. Then we go to total nitrogen. Similar situation. And if you're noticing also our box plots that are green downstream, post study, the variance is also a lot less. We're not getting that very varied data set. So things are staying a little closer together. Again, highly significant. We had a median reduction of total nitrogen of about 64%. Now let's break nitrogen apart. Let's look at just organic nitrogen. Again, our post-study was highly significant, change of about 75%. And again, nitrate, nitrite, 45% median change. This is our inorganic nitrogen, not as high of a change, but still highly significantly different. Then we have ammonia, same thing, about 70% reduction, highly significant, different from post and pre. Then we look at fecal coliform. We also have a change downstream of about 74%, highly significant. A lot of the fecal showed a quicker reduction when the cattle was just fenced out prior to, but this study, unlike the ones that we partnered with NC State, we're not able to isolate, is it the stream restoration or cattle exclusion, but it's pretty significant. Real quick, next to the adjacent trib is T3. You'll see it highlighted in yellow. The red is the watershed. So the total drainage area is 141 acres. So it's about double what you're seeing. I didn't want to put the whole thing, or you would have this tiny little picture. But overall, we did an upstream downstream of the treatment. This reach was primarily, if you notice, orange, enhancement 2 with restoration on the downstream part. So we sampled just above the confluence of where it enters into T4, and we did a pre and post as well. Also, we see some significance, even with the much busier watershed upstream, but we had a median change of 53% and a p-value of 0.0015. So in summary, for the, to just put it in words, what I was just trying to show, Backwater T4 showed it's a low noise watershed with higher signal from the pre-study, and then we could see a change. Most of our parameters had a 64 to 79% reduction compared to pre-construction conditions. Nitrate and nitrite had a 45% reduction. And overall, we saw decreased concentrations and decreased variability among both nutrients and suspended solids. And we could attribute majority of the change to the attached stream reconnect, stream reconnect, vegetated buffers, and cattle exclusion. And then we also saw a significant reduction in fecal coliform between 53 and 70%. And we think majority of that is from cattle exclusion. So what is DMS's goals moving forward? A lot of that was already explained by Greg Melia, so I won't spend a lot of time here, but basically include projects with different levels of signal to noise. We would like to examine the effects of different restoration treatments, calculate and compare discharge and loads, and analyze the change in hydraulic residence time, especially with flooding going on. And then another thing, just to let you know, on our website, we do have a portal. So basically, it's open to the public. You could go to our sites, click on any project. This one here shows Backwater, and you can pick, Crane Creek, Cross Creek Ranch, Stinking Quarter. These are our projects that us at DMS are internally monitoring. And then you could pick your parameter and group it by date. But if you look here on the very top line, that's discharge over the time. Now there are breaks when we didn't sample. If you look at the middle line, that's TN, and it's a scatter plot of basically the same thing you just saw as a box plot. If you look at the dark blue, that is your downstream total nitrogen. You could see how varied and how high the concentrations are. Compared to the next set, there's a break, that's construction. But if you look at I think it's like a fuchsia or like a reddish over the orange, that is the total nitrogen post-study. And you could see that it's not as varied and not as high in concentration. The orange and the green are your upstream site. And of course, the break in between is construction. And then down below, we also put our rain data that we collect on site. And then on the bottom, you can see the different box plots that you choose. And it looks very familiar to what I just showed you all. And then you could actually click on the box plots and see your descriptive stats. And you could run a t-test or a Wilcoxon. But the data is not normal. So I prefer, unless you log transform it, I would probably not. So I would like to acknowledge my DMS Science and Analysis Group, Perry Ann Russell, Greg Melia, Joe Familaro, and Ling Su. And our DMS partner for this project is Wildlands Engineering. Do you have questions?
Yeah, excellent. Yeah, if you have a question, please approach the microphone there. Don't be shy. There's a lot of people here.
And if I can't answer it, I'll have Greg answer it. And if not, you could email me.
I think last slide you talked about discharge. So I was going to ask about
what?
discharge and taking
Yes.
the flow into consideration.
Yes.
Whether you've maybe taken a preliminary look at the data to see. I know you said it was going to be part of your future work.
Yes.
Right?
Oh, you wanted to know if we looked
If
preliminary?
you've taken a stab at it to see if
We
there's,
have, looking at it because they're composite samples, so we would take within that time period. I've looked at discharge and then concentration to figure out a load.
Okay.
Because we're still kind of fiddling around with some of our sites and getting the proper, what's it called, rating curve.
Right.
But for Backwater, we were pretty confident. But yeah, we had like similar reduction, 60, 50% reduction in the total load of nutrients within that time period. But that's preliminary. So I'm not advertising it, but we did look at it.
All right.
And we will like to show that to, a lot of people are interested in how many pounds of nitrogen have you reduced. And it was promising, even though the first year was a very wet year. Second year, No, the second year was a wet year. The first year was not. So you would assume higher loading,
Right.
but it ended up being less. So we hope once we QA everything that stays steady.
Definitely, I'll be following you.
Yes,
on
thank
the
you. Thank
dashboard.
you.
And then the other question I had was about, the post restoration monitoring.
Yes.
How long after the restoration did you start monitoring? I know
About
it takes a while, to get a system to equilibrate.
for the Backwater study, I think it was about 6 months. Greg, you correct me if I'm wrong, but we're thinking about 6 months. Once they're done, they plant the vegetation, and then we will start going out there to monitor. And we take notes. We're just trying to build on all of this. Thank you for the
You're
questions.
welcome.
Oh, we got time for one more if anyone is brave enough to.
They'll end up emailing. There's the email. Danielle,
Save some
Merritt.
emails. Save some emails.
Thanks for the really interesting talk. I just had a couple of questions.
Sure.
You mentioned that there was a eutrophic pond that might be a source, and I was just wondering if that was addressed in the restoration activities. And then a related question is just, you mentioned, I think, levels 1 and 2 restoration, and I was just curious, what that entailed.
Yes, I will. So for the pond, that was addressed. That was up here in that. So below that little channel below the star for the upstream, where it shows enhancement and restoration, the pond was there. So they did address that in the treatment. I will let Greg maybe answer the question on the difference between enhancement 1 and 2, because I'm still learning some of that.
So in North Carolina, thanks. So in North Carolina, in our parlance, restoration means the complete reconnection of the stream to its floodplain. So it's a reconfiguration of the channel in its entirety and returning the floodplain connection to some relic level, inclusive of buffer planting, inclusive of other BMPs like cattle removal and things of that nature. Yes, we did remove that pond. And that's another thing we would like to look at, because a lot of that goes on in mitigation in North Carolina is actual pond removal. And I think we would like to know under what circumstances might they be net sinks or sources. And that's what my question about with the RSC was, when you get algal blooms, your pH can skyrocket, and when it crashes, your DO will go with it. And so in some instances they are, and that one that you saw, that highly eutrophic one, it was a source. But maybe not in every case. It's a good idea to remove these. But you do have the problem of forever, which is if the pond is not maintained and you don't maintain the dam wall, you can have an issue. But the second level, so pond removal is part of that overall restoration effort, and the other levels of enhancement 1, enhancement 2, they're less heavy-handed. They tend to just maybe look at 1 or 2 dimensions of the channel, may not be looking at complete reconnection to the floodplain, may not be looking at creating a new sinuosity or belt width or stream alignment, but would include things like vegetative buffer restoration and BMPs like cattle removal. And so there are different levels of intensity, and our typical projects have a mixture of all of them, including preservation in some cases. So, but since our providers are trying to target the hotspots, often we're doing some level of restoration and enhancement. So, great.
Thanks
Thank you
again,
all.
Danielle, Greg.